The field is sited on an area of drained lowland peat, with drainage ditches running around the perimeter and underground field drains installed throughout. There is a slight natural slope running west to east, falling by 1 metre across the 400-metre length of the field. The field will be re-wet to reduce carbon emissions and a higher water table maintained to grow a crop of typha, also known as bulrushes. The first stage is to install ditch blocks into the perimeter drainage ditch to stop water draining from the field. Underground deep trench bunds will then be installed to break through the existing field drains and to halt the flow of water across and then off the field. Deep trench bunds are created by digging a trench, in this case 2 metres deep, into the peat. This is then backfilled with more peat and compressed. This forms a solid, waterproof barrier, stopping water from draining off-site. A further deep trench bund will then be installed around the perimeter of the field. This will also be raised 0.5 metre above ground to stop any surface water draining off the field. At the eastern end, an additional bund is installed to add a further layer of protection for the train line that runs alongside the field. 2 water storage areas are then created at the lowest point of the field, where the water table is naturally highest. These are approximately 1.5 metres deep and will hold rainfall and provide water to irrigate the field during dry periods. Another series of bunds are then installed, dividing the field into a number of compartments. Each of these additional bunds is 4 metres wide and is also raised 0.5 metres above ground to act as access tracks for tractors and farm machinery. The bunds are spaced so that standard tractor arms can reach across the compartments without having to drive on the wetter ground. A solar-powered pump is installed into each water storage area. This powers an irrigation system to deliver water across the field, maintaining a stable water table. Irrigation pipes are installed inside the main bunds, running east to west. At the junction of each bund, smaller irrigation pipes will branch off to deliver water into each compartment. At each junction, a gate valve will be installed. These can be opened and closed to deliver water into each compartment as necessary to maintain a stable water table at or just below the ground surface. Alongside delivering water into each compartment, excess water can also be removed and fed back into the water storage areas through a series of drainage pipes and weirs. These will be placed at the eastern or downhill side of each compartment. The pipes will run through the wide surface bunds with a manually operated weir at their opening, which can be raised to release excess water or lowered to keep water within the compartment. There will be telemetry water table measurements across the field, informing the farmer of when the irrigation and drainage valves and weirs need to be opened or closed. The field is now ready to be sown with typha seeds. In this instance, the seeds were sown using a specialised agricultural drone which broadcast the seeds from a hopper. 2 methods were trialled to sow the tiny seeds. Firstly, by encapsulating them into clay pellets which dissolved on contact with the water, and secondly, by suspending them in a cellulose gel. The typha seeds germinate within a few weeks and are now established and growing well. The typha will be ready to harvest within 12 to 18 months, and several mechanical harvesting techniques will be trialled. This trial hopes to provide optimal growing conditions for the typha crop, showing that wetter farming could be an achievable and profitable option for some areas of lowland agricultural peat, whilst also providing numerous ecosystem service benefits, such as reducing carbon emissions, improving water purification, and increasing biodiversity.